Linux doesn't trust file names. To know what a file really is, it reads the first few bytes of the file itself, a fingerprint called a magic number. File extensions lie. A file named report.pdf might hold raw text, and an image can sail through with no suffix at all. The name on the outside tells you nothing about what's inside. Magic numbers are short, fixed signatures stored at the very start of a file. A PDF begins with the bytes 0x250x500x440x46, literally the characters %PDF. A JPEG starts with 0xFF0XD80XFF. And YLF binary, the heart of Linux executables, opens with 0x7F followed by YLF. These byte patterns are the real identity of the file. Linux keeps a master catalog of these signatures in the magic database, a set of rules stored at /usr/share/file/magic that maps byte patterns and their offsets to readable type names. A companion file, /usr/share/miscellaneous/magic.mgc, holds the same rules precompiled for speed. When you run the file command, it opens the target file, reads only its first chunk of bytes, walks through the magic database looking for a match, and then prints the human-readable description it finds. No extension required, no guessing. 3 flags make the file command far more powerful. File, I prints MIME types for web and mail handlers. File, S reads block and character devices directly, perfect for inspecting whole disks. File, Z peeks inside compressed archives and reports on what they really contain. This matters because trust is everything in computing. Forensic investigators recover deleted files by their signatures. Security tools catch renamed malware. Servers classify uploads safely. Magic numbers let Linux inspect the truth of a file without ever believing its name. Welcome to a hands-on demonstration of the file command, one of Linux's most reliable utilities for identifying file types. Unlike trusting a file extension, file reads the actual bytes of a file and reports what it really is. Let's open a terminal and walk through real examples. We start with clear to wipe the screen and give ourselves a clean canvas. This isn't part of the lesson. It just keeps each example visually isolated so the output is easy to follow. Running file with no arguments prints a short usage message reminding you that a file name is required. It's a quick way to see the command's built-in syntax reminder without opening the manual page. We clear again so the next examples are visually clean. Now let's actually point file at real system files and see what it reports. Our first real test, file/bin/ls. The command reads the magic bytes at the start of the binary and reports it as a 64-bit ELF executable, dynamically linked, built for x86-64, and stripped of debug symbols. That's exactly what we'd expect for a compiled system binary. Next, file/etc/password reports it as an ASCII text file. That's because the password file is just plain human-readable user account data. No magic bytes, no binary header. File correctly identifies it as pure text. Now file/tmp. But /tmp isn't a regular file, it's a directory. File recognizes this and reports it as directory, with a note that it has mode 1777, the sticky bit. That sticky bit means only the owner of a file can delete it, even if other users have write access to the directory. Here's where things get interesting. We pipe the first 16 bytes of /bin/ls into xxd to see the raw bytes file uses to make its decision. The output starts with 7F454C46. That's the ASCII4.ELF, the magic number every ELF binary begins with. The next byte 02 means 64-bit, 01 means Little Endian, and 00 is the ELF version. This is exactly what file is reading under the hood. Now we try file, I/etc/password. The I flag adds a MIME type to the output, giving you text/plain, charset equals us ASCII. This is incredibly useful when you're scripting file handling, and need to pick the right MIME category for HTTP uploads or email attachments. Finally, file s/dev/sda with error redirection. The S flag tells file to read from block or character special files, which normally cause an error because file refuses to read device nodes. In a sandbox demo without a real disk, the command fails and our echo skip fallback kicks in, printing skip. The lesson: file S is what you'd use to inspect the file system type on a raw disk device like /dev/sda1.